All right. Let me start with some announcements. So this is a makeup lecture we're having because there will be no lectures on September 17th and 19th. So today is one of the makeup lectures, and the second one will be on September 29th. I am flying out of the country immediately after the end of the lecture on Friday at 11. So I will not be able to hold office hours. I have to dash out of here and run to San Francisco Airport. So as a result, I'll have a makeup office hours this coming Wednesday from 11 to 12. The last announcement is that homework number 2 is due on Friday. Okay. Before I get going with today's lecture, are there any comments or questions? How many people think that the pace of the course is appropriate? Oh, yeah. It's not too fast, not too slow. Okay. How many people think it's too fast? Raise your hand. I really want to count that. Okay. And of the people who think they're too fast, how many are undergrads? And of these undergrads, who did you take the 120 with? Yeah?
Yes, right.
And you? And who did you take it? Oh, you didn't raise your hand. How about you guys? So of the people who think the pace is a bit fast, I want to get an idea of what speed I should be going. So one more time, the people who think it's going too fast, I'd like to get a hand up. Okay, who did you take it with? And you too? And how many people think it's too slow? Okay. I'd appreciate talking to the folks who think it's going a little bit too fast at the end of the lecture. Again, it won't affect your grade in any way. I did go over the Gasper notes over the weekend, and I have some idea of what emphasis was put on what topics. But this is a pretty hard course to teach when you have students from so many different backgrounds. So I like to target it so that maximum number of people are happy with it. But if you think the pace is a little bit fast, please come talk to me at the end. Any questions or comments at this point? Yeah.
So where is the meat of this course going to be? Where are we going to spend most of the time?
It's various topics on digital signal processing. And we're going to move from Z-transform to sampling. We've already talked about upsampling. We talked about downsampling, A to Ds, oversampling, noise shaping kind of ideas. Then we move to filter design, filter realization, and move to DFTs and to FFTs, and then filter banks and wavelets if there's time permitting. And then along the line, I'd like to also introduce some applications. So it's a general course in discrete time signal processing. It's supposed to trail 120, and my goal is to not to bore people who already understood and did well in 120, but at the same time not to fall behind people who didn't have as good of a background in 120. But 120 is a prerequisite for this course. Okay. So what I'm going to put the microphone on. What I'm going to talk about today is Z-transform. We're just going to wrap up Z-transform and possibly, if there's a little bit of time, talk about downsampling. So what I talked about last time was I introduced the topic of Z-transform, why it's needed, where we're going with it, and then talked about inverse Z-transform. In particular, if you can put the camera up, is it on? Yeah. So in particular, what we talked about was the concept of inverse Z-transform, which is how to get back the sequence x of n from x of z. And this was the closed form expression that I wrote down for it is 1 over 2 pi j, a contour integral counterclockwise of x of z to the n minus 1 dz. And the question was, what contour should we pick? And the answer is that any contour you pick in the region of convergence of x of z times z to the n minus 1, which is the function we're integrating, any contour in the region of convergence of that is good enough and will give you the same answer. Then, in order to be able to do this contour integration, I introduced what's called Cauchy's residue theorem. And Cauchy's residue theorem says that if f of z, this function, is analytic, that means it's made of poles and zeros and doesn't have complicated singularities. Then you can write this expression for its contour integration. So if I do a contour integration of f of z dz in a counterclockwise direction, 1 over 2 pi j, it looks awfully similar to the inverse Z transform, over a contour C, that's closed contour, any closed contour in the Z domain, that, to evaluate that integral, all I have to do is sum up the residues of f of z at all the poles that it has. That all the poles that, are inside this contour. So if I pick this contour to do my integration, and this function has 2 poles inside it and 1 pole outside, then to evaluate this integral, all I have to do is compute the contributions of the residues only due to the poles that are inside this contour, okay? Not that, even if I have a pole here, I don't compute the residue of that, just these 2, okay? And then the question is, well, what is the definition of a residue due to a pole of a function f of z? And this is it. If f of z has a pole at location z naught, which is of order s, it could be first order, second order, third order, fourth order, and this phi of z is the rest of f of z, the other poles or the other zeros or other junk that are in f of z. Then the residue of f of z evaluated at z equals z naught is given by definition 1 over s minus 1 factorial, the s minus first derivative of phi of z with respect to z, all evaluated at z equals z naught. So that's the definition of a residue of f of z. So combine this with that, you should be able to integrate any analytic function along any contour. Now, one question that could arise is, what if my contour just encircled the origin but only included this P1 pole like this? Then you only compute the residue due to that. What if my contour was this thing? Then I have to compute residue due to this, and due to that. So it's as many poles as inside the contour. And why is it that, so this is Cauchy's, why is it that here it doesn't really matter which contour I pick? Well, because it has to be in the region of convergence of x of z to the n minus 1. And because it's in there, then it's a fixed thing. It doesn't matter. The number of poles that's inside any contour in this region of convergence is always fixed no matter which contour you pick. Okay? Why? Because region of convergences don't include poles, right? So that will become clear when we apply Cauchy's residue theorem to this in just a minute. So I gave you some examples of some simple functions that we did contour integrations on, and now what I want to do is give one more example of Cauchy's residue theorem, and then move on to explain how we can apply this concept to computing inverse Z transform. Okay? So so what we're going to talk about today is inverse Z transform and Cauchy's, in particular, we're going to start with Cauchy's residue theorem. Okay. So suppose then I have a function, so I'm going to start with another example. Suppose I have a function f of z, which is 1 over z minus 2 times z minus 3. So this function has 2 poles. And I'm not talking about taking the inverse Z transform of it. I'm just talking about plain doing contour integration on it. Okay, so it has 2 poles. One is at location 2, one is at location 3. And I want to do a contour, the goal is to compute a 1 over 2 pi j counterclockwise contour integration of along the following contour. Magnitude of z equals 4. That means a circle of radius 4 in a counterclockwise fashion. F of z dz. Okay. So according to Cauchy's residue theorem, both of the poles are inside. This is our contour. This is the contour z equals 4. Because there's two poles of this function inside, I have to compute residue to do both of those. So for z equals 2, f of z, which is given by phi of z over z minus 2, that means that phi of z is just 1 over z minus 3. That's what phi of z is. Because by definition, we said, you look at the order of this pole, this is the order 1, f of z was z minus z naught, which in this case is 2, to the power of s, where there is no power of s, is just 1. S is equal to 1. So that means your phi of z in this case is 1 over z minus 3. So to compute the residue of f of z at z equals 2, it's 1 over s is 1, 1 minus 1 factorial, and because s is 1, I'm not taking the derivative. It's just phi of z evaluated at z equals 2, which is 1 over z minus 3 evaluated at z equals 2, which is just minus 1. So that's the residue due to this pole at location 2. Okay? And now we could do the same thing for z equals 3. So for z equals 3, phi of z is now what? 1 over, I'm sorry, phi of e of z is just now 1 over z minus 2. That means the residue of f of z evaluated at z equals 3 is 1 over 1 minus 1 factorial, 1 over z minus 2, again evaluated at z equals 3, which is equal to 1. So, so if I were to compute this integral, it's equal to the residue due to this plus the residue due to the other one, so it's 1 plus minus 1, which is just 0. So integrating this f of z, or counterclockwise on this contour, will give you 0. And of course, now what if my contour was here? What would the integral be? Let's call this contour C1. The integral here would have been what? Just minus 1. So for C1, we get the integral is equal to minus 1. And then what if the contour was here? Let's call it C2. 0. You get the integral is 0. Because there's no poles. There's no contribution from any poles. And let me do one last example of Cauchy's residue theorem and then move on to applying it to inverse Z transforms. So suppose that I have f of z given by z cubed over z minus a, where a is some pole like at location 1 plus j. So this is the z-plane, and this is 1 plus j. Okay. And so, and we're doing a contour integration on some circle or some contour that encompasses or includes this guy. So once again, phi of z is just z cubed, and the pole z naught is at location 1 plus j, which is a, which is the same thing as this variable a. So all I have to do is compute the residue at 1 plus j, and that's given by 1 over 1 minus 1 factorial again, and then phi of z evaluated at z equals 1 plus j. So phi of z is just z cubed, which is z cubed evaluated as z equals 1 plus j, which is just 1 plus j to the power of 3. So the question that, let me pause at this point before I switch topics just a little bit. Are there any questions on Cauchy's residue theorem of how it works? Yeah. It's a normalization factor.
When you take the answers minus 1, you need to divide it by 2 pi j.
No, the Cauchy's residual theorem says this. It's 1 over 2 pi j of the integral is the residues. So when I say the integral is that, I really mean 1 over 2 pi j of the integral. You have a point here. And this is 1 over 2 pi j. So now let me switch gears and talk about how does this whole thing apply to Z transform. So how to apply Cauchy's residue theorem to Z transform, to rather inverse, to computing inverse Z transform. Well, we have this expression here. What is the expression for inverse Z transform? When I wrote this down as a proposal last time. I never proved it to you, but it's fairly, I'll do that right now, that this is indeed the way to compute inverse Z transform. So by definition, I wrote it down as 1 over 2 pi j, and then counterclockwise contour integration for contour C, which is a closed contour, encircling origin in the region, however, in the region of convergence of whatever function I put here, which we put x of z times z to the power n minus 1 dz. Okay, in the region of convergence of this x of z, z to the n minus 1. Okay. So before I end up proving this thing, I want to make an observation. So you can already see that Cauchy's residue theorem was telling you how to do 1 over 2 pi j contour integral of some function f of z. So that function f of z is now this thing. So you can immediately see how Cauchy's residue theorem can be applied to this. And I'll show you some examples of it again in just a minute. But for now, I want to convince you that this expression is indeed true, and that if I do this contour integration, I get x of n. But even to prove that, I'm going to make an observation, and that observation already uses Cauchy's residue theorem. So let me just write that observation down. And the observation goes as follows. Is that if I have 1 over 2 pi j of counterclockwise contour integration on contour C, which is any closed contour that encircling origin, z to the n dz, then the answer that I get is it's 1 if n is equal to minus 1, and it's 0 otherwise. So which is exactly the same as saying it's delta of n plus 1. It only takes the non-zero value at n equals minus 1. And how would you go about showing that or convincing yourself that that's true? It's pretty straightforward. You can sort of divide it up into two cases. First of all, sort of proof, if you will. If n is positive, like if n is larger or equal than 0, will this function inside the contour integral have any poles? No. So that means, so z to the n would have no poles. That means that whatever close contour around the origin I take, there'll be no contribution to that pole, no residue due to that pole. That means there's no residue. That means, what can I say about the contour integral? It's 0. That means that 1 over 2 pi j contour integral is 0. For n, for this value, it's 0. Okay. So that already proved it for all the positive ends. Let's talk about values of n equal to -2, -3, etc. Let's say n is equal to -2, just for the sake of an example. What I get is, let me go to a new page here, because I don't want to be messing up this page. So could you have half of that page shown, please? Great, thank you. So for n equals -2, what do I get? I want to compute 1 over 2 pi j of counterclockwise contour C, z to the power of -2 dz, right? So what does that mean? Well, that means I have a pole of second order at origin. So that means S is equal to 2, and Z naught, which is my pole, is at 0, and my phi of Z is just 1. So that means I have a second order pole at the origin. So you get 1 over S minus 1 factorial d dz of phi of Z. So S is equal to 2, 2 minus 1, 1, 1 factorial 1, so it is 1. The derivative of CZ is 0. So it's 1 times 0, so it's 0. And you can repeat the same thing for n equals -3, -4. You can easily see that all it is the same argument repeated. Because phi of Z is 1, the derivative of it is equal to 0. And so the only non-contributing term is when n is equal to -1. Okay? In which case, after you go through the Cauchy's residue theorem, you can see that it's 1 over 2 pi j of z to the n dz. Z to the power of -1 dz is just equal to 1. So QED, that means we just proved it, that integral is just delta of n plus 1. And why is it that, because when we have, why is it that it ends up being 1 in this case? Because then phi of, can anybody quickly explain? Because phi of Z is 1, but I no longer take the derivative. You see, for n equals -2, I had a double pole, I had to take a first order derivative. N equals -3, I had to take twice the derivative of phi of Z. But phi of Z is a constant. If I take its derivative once, I get 0. If I get it twice, I get 0. 3 times, 4 times, 5, I get always 0. But when n is equal to -1, just so that for completeness, let's just finish that. In that case, S is equal to 1. So I get 1 over 1 minus 1 factorial, but no longer the derivative. I get phi of Z evaluated at Z equals 0. But phi of Z is just 1, so I get a 1. That's why. It's the S thing is what messes you up, or not messes you up, is what makes the difference. Remember, how many derivatives you take has to do with the order of the pole. If the order of the pole is 1, if you have what's called a simple pole, you don't take any derivatives. If the order of the pole is 2, that means you have a second order pole, you take the first order derivative. If this was Z cubed, you would have taken the second order derivative. Is that clear to everyone? So that's why this thing is true. Okay, now, having made that observation, let's see how we can utilize it in order to compute Z transform, inverse Z transform. Okay, inverse Z transform. So what do I get? I get x of Z is equal to summation over n, x of n, Z to the minus n. That's the forward Z transform. And if I come back here to this page, then I'm going to call this whole thing here the right-hand side. RHS means right-hand side. I want to evaluate the right-hand side and see if I can come out of it, get out of it x of n. So the right-hand side of that inverse Z transform equation, which we're trying to show that the right-hand side equals x of n, is given by what? Well, it's 1 over 2 pi j, a contour integral along C, which is a closed contour encircling origin in the region of convergence of x of Z. Now I'm going to plug in This is the right-hand side equation that we have. I'm going to plug in for x of z this thing here. So what do I get? I get summation, and I'm going to get rid of this dummy index n and put it k. Summation over k of x of k z to the minus k. That's my x of z. And then z to the power of n minus 1 dz. Okay? And now what can I do? Well, I can reverse the order of the integral and the summation. And what do I get? I get summation over k of x of k. And now bring the 1 over 2 pi j inside. And do a closed contour integration of z to the minus k z to the power of n minus 1 dz. Right? I combine these two guys together. And what, combining the powers of these two things, I get z to the power of minus k plus n minus 1. And what can I say about this integral? Now I'm going to plug in my observation, which is shown right here, which says the 1 over 2 pi j of integrating this thing z to the n dz is given by delta of n plus 1. Now I don't have z to the n, I have z to the minus k plus n minus 1. So I just replace the n here with this new thing. So this, based on the observation that we have, this is not delta of n plus 1, but this n has been replaced by this guy. So minus k plus n minus 1, and then the plus 1 here, which is just delta of minus 1 and plus 1 cancel, n minus k. And this thing comes because of this observation we just made. So then this is equal to summation over k, x of k, delta of n minus k. And what is this? When you integrate delta times a function or you sum it, you just get x of n. So QED, I started with the left-hand side and I got a right-hand side and I got my left-hand side, x of n. So using that observation that uses Cauchy's residue theorem, you can easily show why the Z transform, inverse Z transform is given by this. Are there any questions on this? Okay. So let me now that we have this Cauchy's residue theorem, and let me just apply it to compute real inverse Z transform. Real, I mean actual. I don't mean real and imaginary. Actual inverse Z transforms. You have to be very careful about your terminology. So use CRT. And CRT doesn't mean your monitor, Cauchy's residue theorem. But what does that CRT stand for? Oh, of course. There's so many acronyms, you can't remember what they stand for, and you just know what it is. Anyway, use CRT to compute inverse Z transform of the following expression. Let's say I have x of z is equal to 1 over 1 minus a z inverse and 1 minus b z inverse. And so this is a function with a pole at somewhere at a and another pole at b. And so how would I go about computing the inverse Z transform of this? Well, first of all, this is a bit of a contrived example. I don't know how many of you have heard of this. In educational system, we always want the students, when you ask questions from students for exams, you want them to answer it the particular way you were thinking about it. The joke or the story is that there was an exam where there was a Mercury what do you call it, the thing that measures pressure? Barometer. There's a mercury barometer, and the question is, you want to measure the height of this building, use the mercury barometer to do it. And it's an oral exam, and the kid who's supposed to answer, of course he knows the answer, what it is, the simple answer, but then he keeps trying to avoid it. He says, I go on top of a building, I drop it, and I measure how many seconds it lasts. After it breaks, then I know the height. And the teacher says, no, not that way, simpler way. And says, no, then I do something, you set it on fire, and do things. I mean, of course the kid knows the answer. It's the same thing with this inverse transform. How, in real life, if I didn't force you to do Cauchy's residue theorem, how would you go about doing that? Yeah, you do partial fraction expansion, and I'll talk about that in just a minute to refresh your mind, and then you get it done. But now I'm like that teacher. No, not that way, not the easy way. Do it the hard way. No, we're going to use the Cauchy's residue. But the only reason I do that is I want you to see how Cauchy's residue theorem can be applied to this as a matter of principle. Okay. So how would I go about doing that? Exactly. Good. That's what I wanted to hear. I already give you a very ill-defined problem. This function x of v, I can't compute its z transform unless I told you what its region of convergence is. It could be here. How many possible regions of convergence can it have? 3. It could be inside this. It could be between these two. It could be that. So good question. So I'm going to make the case interesting, I'm going to say region of convergence is outside of B. Okay, and I'm assuming that magnitude of B is larger than magnitude of A. So, and I'm assuming that R of C is Z larger than B. Good. So let's just do it the Cauchy's residue theorem way. So x of n is then given by, where is the expression? Yeah, it's x of z, z of n minus 1, dz. So it's 1 over 2 pi j contour integral of x of z is just 1 over 1 minus a z inverse, 1 minus b z inverse, z to the power of n minus 1 dz. And the first thing that you want to be doing is, just to make your life easier, multiply the numerator and the denominator by z squared. So I can write it as 1 over 2 pi j contour integral, and this becomes z to the n plus 1, 1 minus, no, z minus a. I want to get rid of these negative powers, and then z minus b dz. So how do I go about doing this contour integral? What is the answer? How many poles does this function have? Wrong. Wrong. Well, actually, the n plus 1 might not have been so wrong. It's a function of, it depends on n. Why? Because if n is like minus 3, then you have z to the power of minus 2. Z to the power of minus 2 means it's a z square in the denominator. That means you have 2 poles at the origin, and this contour is going around the origin. Now, if I was looking at n minus 5, then I would have 4 poles at the origin. So how many poles does it have? Depends on n. So that's why we do partial fraction expansion, and don't do it this way because it's a pain in the neck. But let's just do it. So consider 2 cases. If n is larger than minus 1, let's say, or equal to minus 1, then there will be no poles at the origin, right? That means there's no poles at the origin. That means that there's only 2 poles, one at z equals a, one at z equals b. And all I have to do is compute the residue contribution due to those guys. So x of n is the residue of f of z, which in this case is this thing, at z equals a, plus the residue of f of z for z equals b. That's what it is. And how do I compute that residue? Well, for this guy, what do I get? I get the pole is it's a simple pole at A, so z naught is equal to A. S, the order is 1, it's a first order pole, and phi of z is just z to the n plus 1 over z minus b. And to compute this guy, what I have to do, it's z naught is equal to b. Again, s is equal to 1, and phi of z is just z to the n plus 1 over z minus a. Okay? And so what I get is x of n is equal to z to the n plus 1 over z minus b evaluated at z equals a, plus z to the n plus 1 over z minus a evaluated at z equals b, which at the end, when you put everything together, it's a to the n plus 1 over a minus b plus b to the n plus 1 over b minus a. So that's it. That's the answer for what? N larger than minus 1 or equal to minus 1. And what can I say about case 2, which is n smaller than minus 1? Let's say n is equal to minus 2. That means I have 3 poles. A simple pole at z equals 0, and then 2 other ones at z equal a and z equal b. When n is equal to minus 3, I have 4 poles. A double pole at z equals 0, and then a simple pole at z equals a and z equals b, etc. So just for the hell of it, let's just consider the case of n minus 2. What happens at n minus 2? So for this case, what I get is f of z is equal to 1 over z times z minus a times z minus b. So then now I have to compute the residues due to these things. So then what happens is that x of n is the residue at z equals 0 plus the residue at z equals a plus the residue at z equals b. Now what is the residue at z equals 0? It's, you go through the whole ragamuffin of, phi of z's and s's and plug in, and you get, it's just 1 over z minus a, z minus b, evaluated at z equals 0, plus this one will be 1 over z times z minus b, evaluated at z equals a. And this one is 1 over z times z minus a, evaluated at z equals b. So I'm not going to go through the math, but after a little bit of algebra, you just get 0. And you can show further that by induction or by other means that the same thing is going to happen for n equals minus 3, etc. So you can show that then x of n is going to be 0 for n smaller than minus 1. Actually, there's another way, there's another way to convince yourself that that's true. Is that plausible? Given this region of convergence, is this plausible that that x of n is equal to, 0 for n smaller than minus 1? Yeah, sure. Because the region of convergence, we already said at the very beginning, is outside of some circle, right? And so what would that tell you about the kind of sequence we're dealing? It's right-handed, left-handed, both-handed, finite length. What is it? It's a right-handed sequence. So the fact that it's from -1, -2, -3 is equal to 0, that's not a surprise. We would have expected to get an answer. So combining these two things, we did it in two cases. One, n smaller -1, the other one, n larger than -1. So combine these answers, then you can case 1 and case 2. And what we get is x of n is equal to u of n, which is a step function, a to the n plus 1, a minus b, plus b to the n plus 1, b minus a. Now, there is another trick. I won't spend any minutes of this class to go over it. There is another way of showing that for n equals smaller than -1, this happens. And that is to change the variables one more time, so that when you do contour integration, you get absolutely no poles inside the unit circle. But I won't go over that. I used to do that in previous years. It chews up a lot of minutes and not all that insightful. Having done this the long way, now let's become like that student who had simple ways of doing things. Let's do it the simple way. Go back to the example. Yeah, question, yeah. Well, no, because the case 1, if you think about it, was page 6 here. Yeah. Case 1, page 7. Yeah, this is case 1. Was n larger than -1? Oh, okay. So you want what happens? Okay, now it turns out that if I plug in n equals -1, these two things cancel each other, and you get 0 anyway. It becomes a special case. Okay, now let's just do this whole inverse Z transform in the simple way, and aliter, which is an alternative way of doing it. Let's use the partial fraction expansion, which I assume you've seen in 120 and 20, possibly. And how does partial fraction expansion work? Well, you say you have x of z is equal to 1 over 1 minus a z inverse, 1 minus b z inverse. And it's, then you write it down. Partial fraction expansion in general works for situations where you have rational functions. That means the ratio of polynomials, p of z over q of z. But you write it down as a over some constant, capital A. Well, let me just use a different letter, just not to confuse it. Alpha times 1 minus a z inverse plus beta times 1 over, beta over 1 minus b z inverse. That's x of z. And what you do is you take a common denominator of those, 1 minus a z inverse, 1 minus b z inverse. So that then the numerator becomes alpha times 1 minus b z inverse plus beta times 1 minus a z inverse. That's our x of z. And based on this thing, this numerator has got to be equal to 1, right? So that means that this whole thing here has got to be equal to 1. That means alpha times 1 minus b z inverse plus beta 1 minus a z inverse has got to be equal to 1 for all z. So this polynomial on the left-hand side has got to equal, for all powers of z, this polynomial on the right-hand side. Okay? And you can do this, what you want to do is you want to equate powers, equate the coefficients of the powers of z minus 1 at the two sides of this equation, on the right-hand side and the left-hand side. What's the coefficient of z inverse on the left-hand side? It's minus alpha times b plus, no, and then minus a times beta. And what's the power of z inverse on the right-hand side? 0. There's no, the coefficient, there's no z to the minus 1 term, so it's 0. And you can do the same thing for other things. You want to equate coefficients of powers of z to the 0, which is a constant term at both sides. So in that case, what's the coefficient of the constant term on the right-hand side? It's just 1, right? And what is it on the left-hand side? It's alpha plus beta. So you can solve, a system of 2 equations and 2 unknowns and get the answer, or you could have solved this thing even easier. There's formulas and packaged ways of doing this, but regardless, this is the most systematic way of doing it. And once you solve it, what you get is that alpha is a over a minus b, beta is b over b minus a, and then and now you have x of z given. Now you can plug these alphas and betas that you found over there, and you get alpha is a over a minus b of 1 minus a is the inverse, plus beta is b over b minus a, 1 minus b is the inverse, and region of convergence is still z larger than b. And now what do I do? Now that I divide, what was the motivation for dividing it into these little fractions here anyway? Because we already know the inverse z transform of these things very easily. It's the same thing over and over. When you don't know how to solve a problem, immediately reduce it to the problem you do know how to solve. And we know how to solve the inverse z transform here. What is the inverse z transform, let's say, of this term? First of all, we apply the linearity property, which is the inverse z transform of sum of 2 things is the sum of the inverse z transform of the 2 things. What's the inverse z transform of this guy? It's an exponential, right? We know the inverse z transform of 1 over 1 minus a is the inverse. It's a to the n u of n, so you can apply that to here. Now, here's where region of convergence comes up. What is the inverse z transform of this? If you didn't know the region of convergence, it could have been, what? 2 possibilities, right? It could have been a right-handed sequence or a left-handed sequence. But now that we know the region of convergence is outside of B, it's outside of some circle, which one do we choose of those 2 possibilities? The right-handed one. So it's something something times u of n, plus the same thing with this. Region of convergence of this is outside some circle, something something u of n. And we get the same answer as before. Okay? So what you do is essentially you reduce it to the inverse z transforms that you know. Now, if this was day 1 and you didn't know the inverse z transform of this, then you could still apply Cauchy's residue theorem here. So Cauchy's residue theorem is a fundamental result, right? It doesn't bank on you remembering the inverse z transform of anything. So it has its own set of values, even though I bashed the other way of computing the inverse z transform. It's too long, too lengthy, but fundamentally, if it was like roll the clock back 1,000,000 years ago and you didn't know the inverse z transform, then nobody had discovered the inverse z transform, that's the thing you would have used. Okay? So before I leave the topic of inverse z transform, so what are, based on this discussion that we just had, what is our bag of tricks, if you will, to compute inverse z transform? So number 1, we just talked about CRT, not cathode ray tube, but Cauchy's residue theorem. We just did this inverse z transform using that. Number 2, partial fraction expansion, which is what we just did. And number 3, what can you do? Series expansion. And what do I mean by that? Well, you can, the simplest way of doing that is to consider expansion. So let's do a little example again. X of z is 5 plus 20 z to the minus 6. I've had many students who sort of in the middle of any exam forget what the inverse z transform is. What is it? Well, all you have to remember is that x of z is summation of x of n, z to the minus n, summed over n. So, which means what? Which means this is, for example, x of da 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 plus x of minus 1 times z plus x of 0 times z to the 0 plus x of 1 times z inverse plus x of 2 z to the minus 2 plus da 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 da, etc. So comparing these two things, what can we say about the inverse z transform here? Well, you can say x of n is what? This polynomial in z is the same as this polynomial in z. You just equate the coefficients for the same powers. What's the one that power of z equals 0 is this guy. So x of 0 is equal to 5. And z to the minus 6, the coefficient for that would be x of what? 6. X of 6 is equal to 20. And all others is equal to 0. So that means x of n is equal to 5 for n equals 0 is equal to 20 for n equals 6, and it's 0 otherwise. So don't forget, this is like this simplest of the methods, the bottom of the pit type thing. But it gives you the answer that you're after. And finally, one other method of doing series expansion, here's another example, is if I give you a hard functions like log of 1 plus a z inverse. This is my x of z, and I want to compute it. How would I go about doing that? Well, first let me explain the region of convergence. Region of convergence is a z minus smaller than 1. And if a z minus is smaller than 1, then it's sort of log of 1 plus epsilon, where epsilon is smaller than 1. And because it's like that, you can look it up in your CRC book. And CRC, I really don't know what that stands for, but I hope you guys, you know what a CRC book is? How many people have used a CRC book before? Oh my God. Okay. Yeah, that's this is the generation of internet students. Look, when you were a kid and you wanted to do, not kid, like a year ago in your college thing, when you wanted to do an integral and you didn't know the answer, where would you look it up? I guess the answer is on the web, right? No? Huh? Short what? Oh, Sham outline series. Oh my God, you've degraded. The students have it. CRC, it has integrals, it has expansions, it has all the physics and chemistry constants, and it's like an encyclopedia. There's one for math, there's one for physics. Yeah.
It is online.
CRT is online. Yeah. Oh, see, I knew it was. But do you guys use it online? No, nobody here uses it online. But anyway, I have the books because I'm from the other. No, I'm not that old. I have the books because when I was an undergraduate, there was only available in books. There was no such thing as the web. But if you go to the web, even do a CRC search. What does CRC stand for, though? Yeah, it's just called CRC. Don't worry about it. It's called CRC Handbook of Math, CRC Handbook of Physics, CRC Handbook of Chemistry, and sometimes they combine them. In fact, the last 100 pages of the hard copy I have is just a log of different numbers. This was before calculators and computers were available. They would list as tables, log of this, log of that, cosine and sines of angles. I mean, I know it's unimaginable for you to have that in a book now. I realize times have changed, but like when I was a student, my professors always talked about slide rule. I said, oh, here he goes again, telling us about the old times. But I've become like one of them, telling you about the old times. But now you can, if you don't know an integral, you can use Mathematica, which is a symbolic way of computing things. You can use, what's the other thing people use? Maple, which is invented at Berkeley. What's the other one? Maxima, right? To tell you what, it gives you the expression for an integral. It's not numerical computation. It's an analytical thing, right? Or you can look it up on the CRC book, either on the web or not. Anyway, make a long story short. If you had a CRC book or looked it up on the web, log of 1 plus x for x smaller than 1, what's the expansion for that? What's the Taylor series expansion? It's x minus x2 over 2 plus x3 over 3 minus x4 to the 4 plus da, right? What other functions have nice series expansions? You can look them up. Sines, cosines, exponentials. Yeah, those are the good ones. So what can we say about this guy then? Well, this is log of 1 plus a z inverse. It's a z inverse minus a z inverse over 2, power of 2 plus a z inverse to the power of 3 minus a z inverse to the power of 4, da. So then x of n will end up being 0 for n smaller than 0, a for n equals 1, minus a squared over 2 for n equals 2, and a cubed over 3 for n equals 3, etc. Why? Because of this expression for x of z. You just write down the expansion. You equate powers of z. So then what it ends up being is x of n is equal to u of n minus 1 times a to the n over n minus 1 n plus 1. Okay? Okay, so any questions? So there's at least three ways that you know how to do inverse Z transform of functions. Now, let me, before I end this lecture, what I'd like to do, so this is really all the discussion we have on Z transform. I'd like to quickly go over the properties of Z transform as a reminder. Again, I'm assuming you've already seen it in 20 and 120. But let's open Oppenheim and Schaefer if you have it. Otherwise, I'll just put it under here and we'll zoom in. Could you zoom in as much as possible? More, maximum. And then just focus to sharpen this. Okay, is that sharp enough? Okay, so let's start from the top and sort of move on to the bottom, if you will. So if x of n has Z transform x of z with region of convergence R of x, and we're assuming x1 of n has the region of convergence x1 of z, it has Z transform x1 of z and region of convergence R sub x1, and x2 the same thing. And so the first property I want to talk about, which you've seen again a gazillions of times before, is the linearity property. A times x1 of n plus b times x2 of n has a Z transform, which is a times x1 of z plus b times x2 of z. And if x1 and x2 have region of convergence Rx1 and Rx2, then the region of convergence for these guys is it contains Rx1 union Rx2. Why does it say it contains? That means it could be a little bit bigger than the intersection. Anybody? There could be some pole zero cancellations between these two. In pathological cases, you could have one of these guys cancel the poles of the other guy, and then the region of convergence suddenly expands. Okay, so that's why it says it contains that. Property number 2, if I shift by x of n minus n naught, which means if I shift by n naught, then the Z transform becomes Z to the minus n naught times x of z, which is, again, you remember that from Fourier transforms, right? You shift gets multiplied by an exponential. And the region of convergence is R sub x, except for the possible addition or deletion of origin or infinity. Why? Because you're introducing poles here, right? And depending upon whether n naught is positive or negative, if n naught is positive, then you have a pole of order n naught, and you have to be worried about new poles that you just introduced at origin. So that's what this talks about here. Next one, the reverse of that. You multiply by an exponential in the time domain, z naught to the n times x of n. And what you get here is x of z over z naught. And this is the region of convergence. And I would urge Dan to prove some of these things, especially the regional convergence, in the recitation, if you can, please, on Tuesday and Thursday. Our next property is multiplication in the time domain by n results in differentiation in the z domain. So n times x of n has a z transform, which is minus z times the derivative of x of z with respect to z. Next one is conjugation. I conjugate x to get x conjugate of n, and on the z domain I get two conjugation, x complex conjugate and then z complex conjugate. Next one is real part of x of n has a z transform, which is half of x of z plus x complex conjugate z complex conjugate. Next one is the imaginary part of x of n, which is 1 over 2j x of z minus x complex conjugate z, the inverse. Next is if you complex conjugate x and flip, do a time reversal, which is a minus n here, you get x complex conjugate of 1 over z inverse. 1 over z complex conjugate, sorry. Next one is the convolution property. I convolve x1 and x2. I multiply in the z domain by x1 times x2. And the last one is the initial value theorem, which I'll prove in just a minute for completeness, which says that if x of n is equal to 0 for n smaller than 0, limit as x of z tends to infinity is x of 0. Now let me just prove that real quickly. So here I'm just going to say, look at table 2 on page table 3.2 on page 126 of Oppenheimer and Schaefer. And now I'm going to let's see, wrap up with the initial what I call initial value theorem. So the only one I'm going to prove is initial value theorem, which goes like that. If x of n is equal to 0 for n smaller than 0, then x of 0 is limit at z tends to infinity of x of z. Can anybody give me a clue how I would go about proving something like that? Just do the series expansion. So let's call this the right-hand side. So right-hand side is the limit as z tends to infinity, and just write down the expression for x of z. What do we know about x of z? It's the summation for n ranging from minus infinity to plus infinity of x of n z to the minus n. Right? And what can we say about the right-hand side? Well, it's the limit at z tends to infinity of, well, let's apply some of our assumptions. Every time you don't apply your assumptions in proving something, maybe they're wrong. The assumption is x of n is 0 for n smaller than 0. So this can become summation from n equals 0 to infinity of x of n z to the minus n. And then you expand that, you get limit as z tends to infinity of, let's write that down. It's x of 0 plus x of 1, z inverse, plus x of 2, z to the minus 2, plus da 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 da. And thank God there's no positive powers of z, because if you have positive powers of z, like z and z squared and z cubed, if you let z go to infinity, those would have blown up. That's why you have this assumption of x of n equals 0 for n smaller than 0. If it wasn't, you would have had, x of minus 1 times z. And then as z tends to infinity, that would have blown up. But now you have all negative powers of z. So z to the minus 1 as z tends to infinity, boom, that goes to 0, that goes to 0. So you just get x of 0. Okay. I'd like to end the lecture in the last two or 3 minutes with one more thing that sort of ties down LTI system, causality, and stability, and ROCs, and Z transforms. It just ties in a lot of things together. Suppose I have an LTI system with h of n given by something. Let's say h of z. H of n, that's the impulse response, and then I take the Z transform of that, then I get the system function. And that system function had a pole, let's say, at 1/2. Let me give you a more realistic example, so that it's a richer example and we can. Right. So with a pole at 1/2, this is the Z plane. What can we say about causality and stability of this system? Is this system causal or stable? And what kind of region of convergence could it have? Well, to begin with, it can have two possible regions of convergences. And what are those? One is Z larger than 1/2, one is Z smaller than 1/2. If I told you the system is causal, what can you say about this region of convergence, and what can you say about its stability? Yeah. So if the system is causal, that means the region of convergence is what? Outside of some circle. Why? Because we know when the region of convergence is outside of some circle, the sequence is right-handed. Right-handed is not the same as causal, by the way. Right-handed means it starts at a non-zero value, and then everything larger than that is non-zero. So you could have causality means h of n looks like this. It's 0 for n, and then it's non-zero later. This is causality. But right-handed means that it could be like that. Don't get confused between causality and right-handed. But if somebody told you it's causal, all causal sequences are right-handed as well. Not all right-handed sequences are causal, right? But somebody told you it's causal, well, it means it's right-handed. That means the region of convergence is outside of some circle, which in this example means Z is larger than 1/2. And what can you conclude about its stability? What does it mean for a system to be stable? That means that its Fourier transform should exist. And what does it mean for its Fourier transform to exist? Well, what does it mean for the system to be stable? It has to be absolutely summable. H of n has to be absolutely summable. That H of n absolutely summable means Fourier transform exists. Fourier transform exists means what? That the region of convergence includes unit circles. So if I know that the region of convergence is this thing outside of it, does the region of convergence include unit circle? Yes. Then I can say, yeah, it's also stable. So if it is causal, because it has a pole at 1/2, it's also stable. Comment number 2, what if I said it's stable? The reverse holds true. That means region of convergence includes unit circle. Okay? That automatically means that I'm in case 1. That means ROC is Z larger than 1/2. And what does that mean? That means H of n is what? Right-handed. Okay? So once you have the pole zero structure of a system and region of convergences, you can make a lot of comments about its causality and stability. Now, there is a famous statement in control that a lot of the mechanical engineering students, for example, or electrical engineering students always say, is that if you want to have stability, you have to have all your poles inside unit circle. That automatically assumes what? Causality. Why? Let me explain that. So So when I say for an LTI system, all poles are, for a stable LTI system, all poles are inside unit circle, I automatically assume causality. So for stable causal LTI systems, all poles are inside unit circle. That's a statement. Why? Well, if I have a stable LTI system, that means that ROC includes unit circle, right? Stable means that H of n is absolutely summable. That means the Fourier transform exists, which means the ROC includes unit circle. That's what stability means. Causality means what? That ROC is outside of some circle. I'm not saying what, some circle. So here's the unit circle. If I know ROC includes that, well, I also know ROC is outside of some circle. So what are the possibilities for ROC? Where is that some circle going to be? Inside here, this is the some circle. Okay? And it has to be a circle. So that means ROC is this. So if it is stable, it has to include this unit circle. If it's causal, it's outside of some circle. So that means that circle is inside the unit circle. And what does it mean what does it mean about the poles? What does it mean about poles of LTI system? Can they be here? No, because ROC cannot include poles. Can it be here? No, it can't. That means it's inside some circle. That means the poles are inside that some circle. And because that some circle is inside unit circle, that means the poles are inside unit circle. Okay? So for an LTI causal stable system, all the poles are inside unit circle. And it all falls through the various definitions of what stability means. Stability means for a system that H of n is absolutely summable, which means Fourier transform exists, which means that ROC includes unit circle. So is this argument clear to everyone? So when you hear people say all the poles are inside unit circle, make sure the causality and stability is stated. If the system is not causal, all of this falls apart. Don't just say for a stable system, all the poles are inside unit circle. You could have anti-causality. If you have an anti-causal system, then what statement is true? For a stable anti-causal system, where are all the poles? Inside unit circle. And for a lot of you, it's hard to imagine how could an anti-causal system exist. When you do image processing, there's no notion of time. So there's no notion of causal and anti-causality. There's just can you process the pixels from left to right or right to left? Did the leftmost pixel come first or the rightmost? None of that. So the notion of, you have a hard time understanding what would be an example of an anti-causal system, but when you do things that don't have time order in them, it's easy to implement them. Even when you have time order, if you pre-record your data, you can do anti-causal processing, you can do all kinds of processing. So I'll just write down the last comment here for today's lecture, which is for an anti-causal stable LTI system, all poles are outside unit circle. The whole argument just flips over. Okay? All right, I'm going to stop now, and on Wednesday, I'm going to start Chapter 4. I already talked a little bit about Chapter 4, the sampling parts and upsampling, but we'll get into it in a little bit more detail. And I'll assign homework on Wednesday, and that homework is going to be due after I come back on Wednesday, September 24th. So you'll have like a, I don't know, a whole 2 weeks to do that homework.